This tutorial focuses only on red-black tree deletion. The search and binary search tree removal are familiar, the hard part is repairing color rules afterward. Deleting a red node is usually simple, because red nodes do not add to black height. Deleting a black node is the problem. One path can become one black node short, so the tree carries a temporary double black marker. Delete fix-up repairs that marker by looking at the sibling. The sibling color and the sibling's children decide whether we recolor or rotate. The rest of the tutorial breaks those sibling cases apart one by one, then finishes with complexity and pseudocode. Before any red-black fix-up, deletion begins as ordinary binary search tree deletion. The trees are still valid red-black trees, but for now we focus on the structural cases first: delete a leaf, delete a node with one child, or delete a node with two children. Color repair comes after that. For a leaf, we simply remove the node. In a red-black tree, the replacement pointer X is the nil leaf that takes its place. For one child, we transplant the child upward. The child becomes the replacement node X for the deleted position. If color repair is needed, it happens after this structural move. For two children, we do not directly remove that node. We can use either the predecessor or the successor. Here we use the predecessor, maximum in the left subtree. Copy 35 into 40's position, then physically delete the old 35 node. The important red-black detail is what was physically removed. We remember its color and the replacement X. If the removed color was black, fix-up may be needed. Now we can see why color matters. The structural deletion step is the same, but the color of the physically removed node decides whether the black height changes. Deleting a red node is easy. Red nodes do not count toward black height, so removing this red leaf does not make any root-to-leaf path lose a black node. Deleting a black node is different. When this black leaf is replaced by an IL, the path through that side has one fewer black node than the other side. That missing black count is the entire deletion problem. Red-black delete fix-up starts from the replacement node X and repairs this deficit. Double black is not a third node color. It is a temporary marker on replacement X, meaning this path is carrying one extra black requirement. Think of it as a deficit marker. The tree wants this path to count like it still has the deleted black node. Fix-up tries to remove the marker. The upcoming cases use recoloring and rotations, depending on the sibling and the sibling's children. In one case, the sibling is black with two black children. Then the deficit is not solved locally, the double black marker moves upward to the parent. If that marker eventually reaches the root, we simply drop the temporary extra marker and keep the root black. Because the deficit has propagated to the top, all root-to-leaf paths are equal again. First fix-up case X is double black and its sibling is red. A red sibling cannot be handled directly, so this case converts the picture into one with a black sibling. Swap the colors of the parent and the sibling. The parent becomes red, and the sibling becomes black. Then rotate around the parent, toward X. Because X is on the left here, we do a left rotation at the parent. After the rotation, X is still double black. But now its sibling is black. We have not solved that yet, the upcoming cases handle black siblings. Next case, the sibling is black, and both of the siblings' children are black. There is no red child available for a rotation. So we recolor the sibling red. That lowers the sibling side by one black node, matching the side with X's deficit. The local child paths now match below the parent, but the parent subtree as a whole is now one black node short. If the parent was red, turning it black absorbs the deficit. If the parent was black, the double black marker moves upward to the parent. Then we repeat the same fix-up cases from that parent position. Next case, the sibling is black, the near child is red, and the far child is black. This shape is not the final repair shape yet. First recolor the near child black and the sibling red. This prepares the subtree for a rotation at the sibling. Now rotate the sibling away from X. Here X is on the left, so the near child is sibling's left child, and we right rotate at the sibling. After that rotation, X still has the double black marker, but the shape has become the far red case. The next case performs the final repair. Final repair case, the sibling is black and the far child is red. The near child can be red or black, it does not change this case. P is the local parent of this subtree, not necessarily the whole tree root. This is the shape that can remove the double black marker. First copy the parent's color onto the sibling. In this example, the parent is red, so the sibling changes from black to red. Then make the parent black, and make the far child black. These are the colors we need before the rotation. Now rotate at the parent, toward X. Here X is on the left, so we left rotate at the parent. After the rotation, the extra black has been paid back. The double black marker is gone, and the subtree is balanced again. Deletion takes O of log n time. Finding the node and doing the normal binary search tree removal follows the tree height, and red-black height is O of log n. Fix-up is also O of log n because the double black marker can only move upward one level at a time. Space is O of 1 for the iterative version, we only keep a few pointers. Start the delete routine with the root and the node Z that we want to remove. Keep Y as the node that will physically leave the tree. Remember Y's original color, because deleting a black node is what creates the hard case. If Z has no left child, this is the zero child or right child transplant case. Set the replacement pointer X to Z's right child. Then replace Z by its right child using the normal binary search tree transplant. Otherwise, if Z has no right child, this is the left child transplant case. Set X to Z's left child. Then replace Z by its left child. Otherwise Z has two children, so we replace its value first. Choose the successor from the right subtree. Now Y is the node that will actually be removed, so remember Y's color. The replacement pointer X is Y's right child, which may be a nil leaf. Copy the successor value into Z, so the search order stays valid. Then physically remove Y by replacing it with X. If the removed node was black, the black height may be short by 1. Call the fix-up routine on X to repair the colors and rotations. Finally return the root after the structural delete and any needed repair. The fix-up routine receives the root and X, the replacement pointer carrying the temporary marker. Continue while X is not the root and still has the double black marker. Find the sibling of X, because every repair case is based on the sibling. If the sibling is red, use the red sibling case first. Recolor and rotate at the parent, which converts the situation into a black sibling case. If the sibling is black and both sibling children are black, use the recolor case. Color the sibling red to match the missing black node on X's side. Move the double black marker up to the parent and repeat the same cases. If the sibling's near child is red, use the near red case. Rotate at the sibling after recoloring, converting it into the far red case. Otherwise, use the far red case. Copy the parent's color to the sibling. Make the parent black. Make the far child black. Rotate at the parent toward X. Now the extra black has been paid back, so remove the marker. At the end, force the root to black. Return the repaired root.